Actually, we have invited to one of the most ideal person to deliver this talk today. So without taking much time, first I would like to invite the President of the Geological Society of Sri Lanka, Dr. Lalin Ranavira, to welcome all of you and to introduce our speaker. Sir, it's over to you.
Good morning to you all. Distinguished members of the Geological Society of Sri Lanka, professionals joining from other organizations, students, ladies and gentlemen. I warmly welcome you all for the public lecture series of the Geological Society of Sri Lanka. Today, our speaker is Dr. Januka Attanayake. Dr. Januka, you are also warmly welcome to this forum. Dr. Attanayake is a research fellow and a lecturer in earthquake seismology at the University of Melbourne, Australia. He was graduated from the Department of Geology, University of Peradeniya, and then he moved to the United States to obtain his PhD in global seismology from the University of Connecticut. For his PhD dissertation, he studies the seismic structure of the Earth's inner core. After his PhD studies, Dr. Januka held several postdoctoral positions in countries like United Kingdom, Portugal, and Germany, where he worked on the structure of the Earth, geodynamics, and seismic sources. He has published many peer-reviewed articles, and he was recognized as one of the 10 most outstanding young Sri Lankans in 2017 by the Junior International Chamber. At present, Dr. Januka Attanayake is engaged in modeling the seismicity in Australia to better understand the governing factors behind the earthquakes in intraplate tectonic settings. Maybe a case for Sri Lanka as well. And he is also a member of the Geological Society of Sri Lanka. Today, we are very glad to have you here, Dr. Januka Attanayake, for this forum. Thank you very much.
Yes, thank you very much, sir. And Dr. Januka, now it's over to you. So before starting your presentation, actually, there are some announcement. After this, after your presentation, there is a discussion session. So participants can raise question during that time. Since due to some technical issues, if you cannot log into the Google Meet, actually there is a live stream through GSSL Facebook page. You can join to this lecture through our Facebook page. Dr. Januka, it's over to you.
Thank you, Secretary GSSL and Lalinza, for inviting me to give this talk to the GSSL membership. It's a real privilege and honor to be able to talk to the GSSL membership. I've been a member since 2002 or 2003, but this is the first time I got a chance to talk to the GSSL members. Thanks very much for that. Yes, let me quickly, I hope people can see it now. Can everyone see my screen now?
Yes, Januka, we can see
yes.
your screen.
All right, cool.
Yeah.
All right, everyone. Yep.
Yes. Yes, go ahead, Dr. Januka. Sorry.
All right, thank you. Thank you. So good morning to everyone, wherever you are joining us from in Sri Lanka. I hope everyone's doing well, despite the COVID situation. But I think it's times like these that, we have to innovate and, resilience is the word that is required at this moment of difficulty. When you're talking about resilience, earthquakes are also times during which we have to exhibit a lot of resilience. So I felt like COVID earthquakes, they kind of go together in that common theme. So today I'm going to talk about dynamic earthquake triggering. I'm not going to talk about Sri Lankan earthquakes. There's an expert in the house, Pasan Herath. He's leading a publication right now. We will be submitting that publication soon to one of the journals, Tier 1 journals. So I'm not going to talk about Sri Lankan earthquakes. If there are any questions, I suggest that we send those questions to Pasan, who is really a geophysics prodigy emerging from the geology department. So in this talk today, what I'm going to talk about is this is a bit of a hobby topic for me. How do earthquakes talk to each other? That's a very fascinating kind of an area in geophysics that we like to learn more about. If you look at disaster statistics coming out of the United Nations Disaster Risk Reduction Office, disasters are increasing, and over the last 40 years, they have increased massively if you look at these numbers. And specifically, if you look at disasters by type, obviously people, the most number of people are affected by climate-related disasters, as you can see on this figure in the top panel. But when you look at fatalities, earthquakes are, hands down, is a #1 killer. And this is for between 2000 and 2019. And that percentage has increased by 3% from the prior 2 decades. So these numbers are going up. So we have a fundamental, duty as scientists to understand, these disasters better. And, for people like me who work in earthquakes, to understand earthquakes better so that we can be prepared and we can serve the community in our own way. So my plan for today is this. I will first talk about stress on faults. I understand that potentially there are a lot of students. If I can inspire a few of them to take up seismology and do a PhD, that would be, my duty fulfilled today. I'm specifically talking to students in this talk. So I'm going to start off with a very fundamental look at the stress on a fault. How does stress on a fault determines timing and magnitude of earthquakes? And then I'm going to jump into 3 classic examples. One is Denali earthquake, Landers, and the Indian Ocean earthquake in 2012. And then I'm going to quickly go over some basic physics behind dynamic triggering. And also, I understand that there may be a few people from places like GSMB here. So for them, more than fundamental research, what's important is operational value of studying dynamic triggering of earthquakes. And I will go over very briefly about the operational value of studying dynamic triggering. All right, so let's look at the textbook look at faults and earthquakes. We know that Earth is a very dynamic place. It's it's in motion all the time, and external stresses are accumulating on weak zones in the crust, and that external stresses exceed internal friction, rupture, fault rupture can happen, and that's the origin of earthquakes. And this little simple model is how we use to explain earthquakes, for example, in subduction zones, not only in subduction zones, but also in intraplate regions. So the point to remember here is that whenever the external stresses imparted on the crust or weak zones by different geophysical processes, then earthquakes occur. if we try to understand this in terms of stress over time versus strength of faults, this is a very idealistic model. What you see here is that stress is slowly building up over time. And when it reaches the strength of the fault, it suddenly drops. And that's when an earthquake occurs. So, and it drops to the ambient stress field. And it keeps going on and on and on if other conditions don't change. So there's a slow loading period followed by a sudden, stress release, which we call an earthquake. So in this model, fault strength is held constant over time, and then stress loading is also held constant over time. And as a result of that, the recurrence interval, the time between two earthquakes, is also constant. So this is a very idealistic, simple model that we use to explain the occurrence of earthquakes. The question is, are there real examples of this model working in the environment? Well, the closest that we can think of is the Parkfield segment of the San Andreas Fault, which is the red shaded region in here in this map. And in this part of the fault, roughly every 22 years, give or take a few years, there's a magnitude 6 event. And when that earthquake came in 1966, people were expecting the next earthquake to occur somewhere between 1988 and 1993, but that event never came during that time. Instead, it came in 2004, more than a decade later. So you can already see that, although we have this idealistic stress versus time versus a strength model, it doesn't actually work exactly as shown in textbooks in the real world. Now, one of the characteristic, and this model of having constant recurrence intervals, constant magnitudes, are called characteristic earthquake concept because they are characteristic to that particular segment of the fault. And one of the features of this concept is that the earthquakes have to break the same part of the fault. So how do you know that it's breaking the same part? You look at seismograms between different events. As you can see here, this is a seismogram from 1922, 1966, and 1934. What you see here is that these seismograms are pretty much one-to-one. So this tells us that, yeah, it's very likely that these three earthquakes broke the same part of the fault. But more recent analysis, more sophisticated analysis, like the one that I've shown down below on the right, inverting seismic waveforms for finite faults. What are finite faults? Finite faults are basically showing slip distribution on the slipped fault. So if you look at this figure down right bottom, warmer colors, reddish, yellowish colors show higher slip, and cooler colors show lower slip. And what you immediately see is that between 1966 and 2004 earthquakes, these the ruptured parts are not the same. They don't overlap. So again, this is telling us that this characteristic earthquake model is not ideal. What you see in the bottom panel there is aftershocks between the two earthquakes. Red is for 1966 and blue is for 2004. What you again see is that they don't overlap. So this tells us that, between 1966 and 2004, it's not the same fault fault segment that ruptured. And then if this idealized model is actually how earthquakes work, earthquake prediction becomes a walk in the park, because we can precisely predict when an earthquake would occur and what the magnitude would be. We all know that that's not true. No one can predict earthquakes. If anyone is claiming to predict earthquakes, he or she is lying through their teeth, or they don't understand physics of faulting. In reality, this is what the stress, time, strength, curve looks like, relationship looks like. All three parameters are nonlinear and they're changing over time. The loading, stress loading, strength, and the stress drop. All these three parameters are changing over time. So what does that do to earthquake prediction? It makes it impossible, because recurrence interval is not uniform, nor is the magnitude of earthquakes. Why is this happening? There are several mechanisms at play here, but in the interest of time, I'm not going to describe all mechanisms. I'm going to just, as an example, show you one mechanism called stiction. Stiction is pretty popular in physics. It's basically tells us that when something sticks for a longer time, friction increases. And these curves are from an experiment, a lab experiment from the early 70s. So this has, we have known this for nearly 50 years now, that when a fault is static, that is, when there are no earthquakes on the fault, friction on the fault increases. And all of these panels show this result under different normal stresses. So the idea is that, if friction is increasing over time on a fault that is not moving, then strength is also increasing. But, there are counter mechanisms that will lead to reduction of frictions. I'm not gonna, like I mentioned, I'm not gonna talk about all these mechanisms. It's just that you have to remember that there are other mechanisms occurring along the fault that gives rise to the strength, stress drop, non-linearity. So today my focus is on faults that are really at this critical stage. What happens to these faults if an external perturbation is introduced? Two things can happen. One is that what happens when you increase the stress rate? The fault will rupture earlier than under normal conditions, and that's because it will reach strength at a much earlier time. And here that earlier time is indicated by minus delta t. So time to rupture decreases if you increase your stressing rate. And the opposite can also happen. What happens if you reduce your stressing rate? And that will lead to an increase in time to rupture. And here it's indicated by plus delta t. So both these mechanisms are possible. For some part of the time, the fault might undergo plus stressing rate. And then for the other part, it might undergo minus stressing rate. So there's a competition between plus and minus stressing rates, and the rupture time is actually a combination of these two competing processes. So what is dynamic triggering? It's simply triggering of secondary earthquakes because of the passing seismic surface waves from a primary event. What does this look like in seismograms? It looks like something like this. If you look at the top panel here, this is the seismogram recorded at Bozeman Station in Montana. This is the surface wave part of the earthquake that occurred in Denali that had a magnitude of 7.9. Denali is in Alaska, and this was a pretty complicated rupture. In fact, it ruptured 3 segments of the fault, Denali fault, that people previously thought that cannot link up, but actually in this event they linked up and produced a magnitude 7.9, and this is comparable to the 1906 famous San Francisco earthquake that wreaked havoc during that time. But in this instance, there wasn't as much damage because this is a remote part of the world. So damage was pretty less. And it comes back to what I started this presentation with, disasters are increasing, but disasters are increasing because of the interaction between hazard and people. When there are no people, there are no disasters. So what I'm going to show you next is really fascinating. The Bozeman station is located 3,000 kilometers from the Denali fault, where the earthquake occurred. And when you filter that seismogram that I'm showing you here, something really strange comes up. And this happens when you filter your seismogram at higher frequencies. Now, the blue seismogram here, like I mentioned, it's the surface wave. Its frequency content is usually less than one hertz. But the seismogram that you're looking at is the same seismogram, but filtered at higher frequencies. In this instance, it's between 4 and 19 hertz. What you're seeing here is a whole bunch of blips showing up. And all these are tiny earthquakes occurring around this station in Montana. These are local earthquakes. How do we know that these are earthquakes? If you look at one of these blips, you can clearly identify a P wave and an S wave. So these are locally triggered earthquakes by this incoming surface wave. And this is what dynamic triggering is all about. You apply a perturbation to existing faults that are possibly at the critical state in the stress time figure that I showed you. And with this little push that they're getting from this surface wave, the faults are rupturing. And this has been observed, at various locations in the US from the Denali earthquake. And this map shows some of the places where triggered earthquakes have been detected. Now, where did all this start? Where did dynamic triggering come from? Well, it first was detected in 1992 in a place called Landers, associated with the Landers earthquake. The earthquake gets the name from the name of the nearest city in Southern California. What you see here is what we call the static stress change. Now that's different from dynamic stress change. Static is the permanent stress change imparted by an earthquake on the crust. So this stress is gonna, stay in the crust for a long time to come, perhaps hundreds or thousands of years. But dynamic stresses are really, last for like hours, not days. But what you see here is that static stress has changed in the crust after the Landers earthquake, a magnitude 7.3 event in South California. And the Landers ruptured a previously unknown fault. As you can see, San Andreas fault is running just to the south of the Landers earthquake. So a lot of people think that crustal deformation occurs only along plate boundaries. It's not. deformation is distributed along wide zones around fault boundaries, plate boundaries. So this is a classic example of that. So what you see here is that red regions have increased static stress, whereas blue regions have suppressed static stress. So you would expect earthquakes to occur on regions colored in red, and not so many earthquakes in regions colored in blue. In fact, if you can remember, in 2009, there was this twin earthquake that occurred in California, two of the largest earthquakes to occur close to Los Angeles, the Ridgecrest Earthquakes. So it was a double event. A foreshock of magnitude 6.4 occurred, and within like 35 hours from that, magnitude 7.1 earthquake occurred. So I'm showing you right at the top corner there, the magnitude 6.4 foreshock, and that is in the region where the stress is heightened by the Lanka's earthquake. So potentially, Lanka's earthquake was responsible for triggering the 2019 twin earthquakes. So Lanka's alone is not a single earthquake. Actually, it was a very complicated sequence of earthquakes. It started off just south of Lanka's. The Joshua Tree fault went off on April 23rd of 1992. That was a magnitude 6.1 earthquake. And then Lanka's went off 5 days later in June. Again, not 5 days, 2 months later in June 28th. And just 2 hours after that, another fairly large earthquake, the Big Bear 6.2 earthquake went off. And we believe that Big Bear is an aftershock of Lanka's. So this is not a simple single earthquake going off. It's a sequence of earthquakes. And all these black little dots are aftershocks. And the aftershocks cover something like 200 kilometers by 100 kilometer region. So this is a pretty massively impacting event. And then following this earthquake, seismic rates. So this figure on the right shows cumulative number of earthquakes over time at different locations in the US, Western US. And what you see here is within the parentheses in that figure, what you see is distance from the Lanka's earthquake to these regions. It starts off from 165 kilometers and goes down all the way to 1,250 kilometers in Yellowstone. And I've also marked two times in that map, Cape Mendocino, the magnitude 7.1 earthquake that occurred in Northern California, and Lanka's magnitude 7.3 event. And you clearly see that the seismic rate is increasing all the way up to 1250 kilometers from the Lanka's earthquake. And all these earthquakes are dynamically triggered. Now, can they be statically triggered? Static stress works only within a couple of fault lengths from the epicenter. So static stress cannot propagate for large distances. Instead, it's the dynamic stress that can propagate for large distances. Now, we can look at qualitatively at seismic rates, but also if we want to be more rigorous, we can also look at statistics of seismic rates. Was there an actual break in the seismic rate? And you use statistics like the one that I'm showing you here. This is called the beta statistics, and it builds up the statistics based on the seismic rate before and after an event, and it can tell us whether the seismic rate increase following an earthquake is actually significant. Now, I'm not going to go into too much detail into this, but I wanted to show you that you can detect dynamic triggering visually, like the figure that I've showed you in the right. Also, you can look at statistics to confirm that. So next example is the dynamic triggering by the Indian Ocean magnitude 8.6 event. This probably is my favorite earthquake, intraplate earthquake in recent times. And this, I hope quite a number of you would remember this. This occurred in 2012, roughly about 120 kilometers from the Sunda Andaman subduction zone. And this is, for that reason, is called an intraplate event. This did not occur in the subduction zone itself. It occurred at 2:10 p.m. Sri Lanka time, and 2 hours later, another magnitude 8.2 earthquake occurred just south of the magnitude 8.6 one. Both were strike slip events, and both were earthquakes that actually broke records. In fact, the magnitude 8.6 earthquake is the largest ever recorded in terms of an intraplate earthquake, and the magnitude 8.2 is the third largest intraplate event ever recorded. So both these earthquakes are pretty significant and pretty big. Now, people have looked at their rupture from different angles. Some people have looked at energy radiation at the epicenter using back projection techniques. These are, pretty advanced computation techniques used in seismology. They can actually look at how the energy at the epicenter migrated over time. And what we generally see from these back projection studies is that the rupture migrated to the west. And that migration region is roughly about 150 to 200 kilometers. So it looks like looking at these back projection results, it looks like the earthquake jumped from one fault to another. And here's another study looking at the rupture from using surface waves, and they identify at least two sub-events. One is a magnitude 8.3, and the other one is a magnitude 8.5. So surface waves also tells us that numerous faults were involved in this rupture. And here's in the bottom right, here's a more advanced seismic inversion for the source. What you see here is the inverted results from GPS data as well as seismological data. So what they find is that at least 1, 2, 3, 4, 5, 6 faults broke during this rupture. And there was this one fault that is about 100 to 200, 150 kilometers away from where the rupture actually started. So there was a pretty big jump in the rupture from where it started. And this remained one of the most complicated earthquakes, ruptures, until Kaikoura earthquake occurred in New Zealand a couple of years ago. And also people have looked at finite faults, that is slip distribution on these different faults. In this study, they have looked at 3 faults, F1, F2, F3 denotes the 3 faults that they looked at. And the key idea here is that this earthquake broke the entire lithospheric thickness, which is pretty significant. Breaking the lithosphere is not easy. It's one of the hardest material that you'll find on Earth, but it broke through that as well during this earthquake. So don't forget that the earthquake occurred in the Warton Basin. Warton Basin is only about 6 kilometers thick, the crust, and below that is all lithosphere. And for lithosphere to break, a lot of stress might have accumulated during this time. And coming back to dynamic triggering, people have looked at dynamic triggering from the Indian Ocean earthquake. And what this figure shows is the figure on the top left show the dynamic strains that were generated by this earthquake. Red shows high dynamic strains, and purple regions show low dynamic strains. You would expect larger perturbations to stress in red to yellow regions and very small perturbations in purple regions. And Fred Politz at USGS looked at earthquakes soon after this earthquake, and all these black circles that you see in that figure are earthquakes that were triggered by the dynamic stressors that were imparted by the 8.6 earthquake. And all these earthquakes are over magnitude 5.5. So large earthquakes can be triggered if the perturbation, the orientation of the stress perturbation is correct, and if the primary earthquake is as large as a magnitude 8.6. Now, he also looked at magnitudes 4.5s and larger, and he did a little bit of Gutenberg-Richter relationship analysis. What he finds is that 6 days following the earthquake, there were the seismic rate increased, as shown here in these red dots, and the background rate is somewhere around here. And these were computed from earthquakes that were occurring prior to the earthquake, to the main earthquake. So the number of earthquakes seem to have increased soon after this magnitude 8.6. And here's another way of looking at dynamically triggered events. He looked at magnitudes 5.5 and larger events, but he selected only the ones that were recorded at distances greater than 1,500 kilometers. And you clearly see here's where the earthquake occurred, the 8.6 event occurred, and immediately soon after you see a jump in the seismicity, particularly these large events. And there have been other studies done to detect dynamically triggered events, and this is one such event by Johnson and Rowland. They also looked at large events, but they looked at magnitude 6 or greater events. And here's an example of the figure that you see in the bottom is an example of the increased seismic rate following this event. And this, the red line here, the first dashed line is the time of the magnitude 8.6. And the second dashed line is the time of a magnitude 7, I'm sorry, it's a 6.7 event. But what you see here is that, the maximum magnitude earthquake, the magnitude 6.7 didn't occur immediately after the magnitude 8.6. Instead, there was a gradual buildup of seismicity. So these are significant earthquakes occurring well before the magnitude 6.7 event. So this, suggests that, there's a cascading, there might be a cascading effect of triggering events. That is, one event, when one event is triggered, it could trigger another, and that event could trigger another, and so on until a big event occurs. So this is another kind of a hazard that we have to be aware of when we're thinking of dynamic triggering. And, Southeast Asia wasn't spared. dynamically triggering earthquakes were occurring in the Southeast Asia as well. Here are some examples from 3 stations. As I showed you in the Denali example, there's the surface wave that you observe at low frequencies, but when you filter these seismograms to higher frequencies, you begin to see these small earthquakes occurring all over the place. And you see that happening in all these seismograms. So dynamically triggering earthquakes are not rare. It seems that, you know, if the stress conditions are right, they are ready to go. So it seems like, you know, dynamically triggering earthquakes have 2 modes of operation. One is that at the time of the arrival of the surface wave, they can go off, or it could, you know, it could be a delayed response. Now, why is the delay? Several things can happen. The strength can change. As I mentioned, the friction on a fault is not constant, it's changing. And in certain instances, we see that as the fault gradually begins to slip, friction also goes up. So that scenario kind of, you know, have it's a competing mechanism where slip is trying to rupture the fault, and friction is trying to hold back it from rupturing. So that can happen in a fault, and that could delay the triggering. And then you have fluid migration, you know, with shaking of the crust, fluid can migrate into the fault surface, and that can lubricate the fault, and as a result of that, the fault can go off at a later time. And then there's aseismic deformation. Shaking can excite aseismic movement on the fault. These are not generating earthquakes, but a gradual slip on the fault. And that gradual slip will eventually lead into a faster fault rupture. So different mechanisms can delay the triggering of earthquakes from you know, remotely. Now, we've done some work on this as well. I suggest that if people are interested in our work, I suggest that you look at this. We've published some work, and I've been, you know, really lucky enough to do some media work around these earthquakes as well. All of these are on my website, so if you are interested, just have a look at these. All right, so getting into the physics, I'm not going to talk at length on physics because physics can get really complicated, but I'm going to try to explain the concept behind dynamic triggering. So this equation, I'm pretty sure almost all of you are aware of this equation. You've learned this equation in your geology courses. What this tells us is that gamma is the Coulomb stress, and tau is the shear stress on a fault, mu is frictional coefficient, sigma is fault normal stress. So tau there is trying to, you know, move the fault, that's the shear stress, whereas sigma and mu are trying to hold it in place. So there's this you know, competition always between shear stress and normal stress. And when gamma reaches a certain value, the fault will go off, the earthquake will occur. So in the context of dynamic triggering, what we are looking at is how much of a perturbation is needed to make the fault slip. So at times of surface waves passing through a fault, what you're actually changing is the shear stress and potentially the normal stress. Friction can also change. I haven't included that in this little equation. And also pore pressure can also play a part. I haven't considered those in this little simple idealistic you know, equation, just so that I can keep things really simple. So if we try to put this in the context of Rayleigh waves, we know that Rayleigh waves are elliptically polarized, and they are polarized in the vertical plane, here indicated by the Z, Z and X axis. And the wave is propagating from left to right, whereas the particle motion is retrograde. It goes, backwards relative to the propagation direction. So the displacement from a Rayleigh wave can be explained by this, simple equation. U is displacement at some distance. A is the initial. You can consider that the initial amplitude of the surface wave. Kx is wave number. These are really simple parameters. Omega is frequency, angular frequency, and T is time. So you can define these equations for Z, Z, and X directions. But what we can do with this is that we can actually estimate the strain tensor if you can estimate Ux and Uz. Actually, Ux and Uz are actually observations. These are the observations that you make on your the recordings on your seismometer. So basically, if you differentiate your displacements, you can easily construct the strain tensor, and then from strain tensor, it's pretty easy to get at the stress tensor, because strain and stress are related by a constitutive law. That is, that's just a bunch of expressions connecting stress to strain through lambda and mu. We call them Lame parameters. What they actually do is they are really explaining material properties of the wave propagation medium. And once you have the stress tensor, then you just resolve your shear stress and normal stress on the fault. This is really simple. Again, it's just a tensor rotation. And then once you do that, you can come back to this equation here. That will, now you have your normal stress, your shear stress, and you can estimate the Coulomb stress variation, excited by your Rayleigh wave. So this is the simple physics behind estimating stresses in dynamic triggering space. So next, this is the final topic. Is there an operational value of understanding dynamic triggering? Well, it's early days yet, but it looks like there are really important relationships that we can draw from studying dynamic triggering. And I'm going to show you one such example here. Now let's imagine that we can fairly accurately estimate N, that is triggering intensity, we call this. You estimate your seismic rate after an earthquake occurs, subtract by the seismic rate that prevailed before the event, divide that by that same before the event rate, you get the triggering intensity. And then if you can relate your triggering intensity to peak ground velocity or peak ground acceleration at a station, you might be able to come up with a relationship. In fact, it turns out that there is a relationship between N and peak ground velocity or acceleration. And that's what this figure shows here. So the horizontal axis is peak dynamic strain. You can roughly think of this as peak ground velocity. And in fact, PGV is also given down here. And the red regions here, the red data points, are those earthquakes that have been triggered at distances greater than 800 kilometers. So the peak ground velocities are really tiny. We're talking about 0.01 centimeters per second velocities, particle velocities triggering earthquakes at really large distances. And here, these are the local aftershocks triggered within a 6-kilometer radius from earthquakes. And it looks like there is a relationship, a linear relationship, it looks like. And once you establish this relationship, we can get into a form of earthquake prediction. It's not the prediction that we think of, that is a specific time or a magnitude, but it's something that can be useful. So what do I do? Let's imagine that you recorded an earthquake, a distant earthquake, a magnitude 8 in the Pallakkale station, and it recorded a peak ground velocity of, let's say, 1 centimeter a second. That's roughly here. That's, yeah, roughly one centimeter a second. And if you have established this relationship for Sri Lanka or for the Pallakkale region, what you can immediately do is that you can look this relationship up and then predict the number of expected triggered events in the region. So it is important because unlike in other parts of the world where earthquakes are ubiquitous and people are used to magnitude 2s and 3s, Sri Lankan people are not really, they're really scared of even magnitude 2.5s or 3s. Particularly, I guess that's the impact of the magnitude 9 event in 2004. The psyche of people are a bit different than it was before 2004. So if we can come up with this relationship, and if we can tell people that yes, there was a pretty big magnitude earthquake that occurred, and we are expecting this many earthquakes in the upcoming week or month or the year, you can make that forecast. It's not actually a prediction. You can make that forecast if we can really robustly establish this relationship. And then you can go further. You can start talking about probabilities of triggering, and potentially, if you go further, you could probably come up with triggering intensity maps like these for known faults in Sri Lanka. So with that, I am going to stop with, here's a little summary for you to think about. Disasters are increasing. Always remember that what we define as a disaster is an interaction between hazard and humans. Disasters don't exist in its alone. And earthquakes are the #1 killer in natural disaster space globally. So that's a pretty good message to get across. And hopefully I've convinced you that dynamic triggering can produce large events, and there is a risk of cascading hazards as well. But these large events don't occur all the time. But if we look at small events that are being triggered from large events that are occurring at large distances, that gives us a very nice window into studying earthquakes. For one, it tells us that where the faults are, and two, they can give us an idea about how much stress is needed to set a fault off in that particular region. So you can get two pieces of pretty important information if you study small events. And then there are operational uses as well. But for that, you have to collect data, build these relationships between triggering intensity and PGB. So with that, I think I'm going to stop. I'd be happy to take a few questions.
Dr. Januka, so it's a very interesting and impressive talk. I think now it's time for discussion. So participants, you can ask questions.
I might have taken more time than I had anticipated.
No, it's quite okay, Dr. Januka. That's very fine. Thank you for your interesting talk.
Dr. Dharmape, can I ask a question?
Oh, yeah, sure, sir. Sanjay, sir, you can ask. Go ahead.
Yeah. It's a very nice talk, Januka. Thank you very much for that. I'm very happy to see you. Actually, I missed your very early part of the question, the talk. Sorry about that. But my question is, how do you assess, or if for a layman, if someone asks, what is the risk for earthquakes for Sri Lanka? How do you answer for a layman? Because there is a public concern in Sri Lanka. Some of the people are fear of a risk of earthquakes, potential risk in the future. So what is your general answer for that?
So yeah, so one thing I think people should understand that earthquakes can occur wherever. Okay, so there's this misconcept that earthquakes occur only along plate boundaries. That is absolutely incorrect. Earthquakes can occur wherever there are weak zones in the crust. So particularly for regions like Sri Lanka, where the crust is really old and has undergone many cycles of deformation, there could be weak zones existing deep beneath, right beneath our feet. So any of these faults can go off at any time. But if you look at the recent history, we don't have a record of large earthquakes occurring. Even there is this record of a magnitude close to magnitude 6 earthquake in 1616 or some around that time. But that too is interpreted by a non-specialist, right? So there's no reliable information of large earthquakes occurring in Sri Lanka. Maybe there are magnitude 5 events, but not more than that. But that's not to say that large earthquakes cannot occur. But it's all the more reason why we have to study seismicity. We don't know much about the Sri Lankan crust in terms of seismicity. We only have 3 stations continuously monitoring seismicity. That's not enough. I think Passan will show in the near future that earthquakes are occurring all the time, in particularly around dams in Sri Lanka. So the risk of a very large event based on the record we have is very, very low. But earthquakes are occurring all the time in the Sri Lankan crust. But majority of these earthquakes are not felt.
Yeah, thank you for the answer.
Thank you, Sanjay. Thank you for your question.
Yeah, thank you very much. I think now, Professor Ilagirana, sir, now you can ask your question.
Very interesting talk. Can you hear me, Januka?
I can hear you, sir.
All right, very interesting talk. Congratulations. And my question is that in your conclusion at last, you said the earthquakes are the #1 killer. But the thing is, does it not depend on the seismic monitoring people do and the seismic design of buildings? Because recently, actually day before yesterday, I'm doing the seismology lectures here. And now the students may think that I've given them wrong information, because I showed a table from Stein and Weiss's book. It said that earthquakes kill only 9 people in the United States, whereas the heart attacks kill more than 33,000 people per year. So
Yes.
earthquakes are the least important thing that appears. But you say number one killer, but don't you think that it depends on the country and the monitoring, all that?
Absolutely. So there's a difference between, I think, the statistics that I'm talking about and what you're talking about. I think what you're talking about is people dying from direct shaking. So I think this is what Stein and Weissation talks about in their book. People actually don't die from direct shaking. It's what you said is correct. It's the shaking. It's the collapse of buildings induced by shaking that kill people. So that's a finer angle to disaster management. But in the context of UNDRR, United Nations Disaster Risk Reduction Program, they are looking at building collapses, deaths from direct shaking, all that together. So that informs where and how earthquake preparedness should take place. So people don't die directly from shaking; they die, but not in massive numbers. But it's secondary impacts of shaking that kills people.
Okay, thanks.
I have to send you regards from Mike Sandiford, LRK, sir.
Okay, thanks. You might just improve.
Yeah, I will.
Right, I think I have another question.
Okay, thank you.
Dynamic triggering, right?
Yes, go ahead.
Now, how long is this going to be active after a major earthquake? Like, for example, the 2012 earthquake you mentioned in the Indian Ocean. Now, is it just happening only a few years after that? I mean, is the possibility exists until what time is going to happen? These induced ones going to happen? Is there a time frame? Is this still being researched?
So there are no specific times. The delayed triggering can occur 2 weeks to months, not years maybe, but there are other mechanisms at play like viscoelastic relaxation. In fact, the magnitude 8.6 earthquake that I talked about is believed to be a result of viscoelastic relaxation of the mantle, stresses imparted by viscoelastic relaxation after the 2000 event. There are models showing that, stress from viscoelastic relaxation peaked around 2012 after the 2004 event. So dynamic triggering, in the context that I talked about, it doesn't last that long, but there are other mechanisms that can actually, hit you years after the main earthquake has occurred.
So the triggering is mainly caused only by the surface wave, not by the body wave, right?
The amplitudes are too small because much of the energy is transmitted through low frequency waves, and surface waves are low frequency waves.
It's because of the long wavelength. Is it causing a warping of the crust? Is it something to do with it?
No, it's actually imperceptible, even at decent distances like 200 to 300 kilometers. You're not seeing waves that you see in Hollywood movies. If you watch the movie San Andreas, you see a huge wave, propagating along the surface of the crust. You don't see that in actual earthquakes. It's a myth. It's just maybe a couple of centimeters max.
Thanks, Januka. Thank you very much for your answers and really stimulating. Thank you very much.
Thanks very much.
Okay, thank you very much, Elaga sir. I think we have a few minutes for quick questions. One or two quick questions.
Along the surface of the crust, you don't see that in actual earthquakes. It's a myth. It's just maybe a couple of centimeters max.
Thanks, Januka. Thank you very much for your answers and really stimulating. Thank you very much.
Thanks very much.
Okay, thank you very much, Rayleigh sir. I think we have a few minutes for a few quick questions, one or two quick questions.
Dr. Dharmapriya, Dr. Tissamana Singh has raised it.
I think initially he tried to ask some questions. So, Tissamana Singh sir, are you available? Yeah, yes, sir. I think we cannot hear you. Still not.
Dr. Dharmapriya, Dr. Tissamana Singh has raised it.
I think initially he tried to ask some questions. So, Tissamana Singh sir, are you available? Yeah. No sir, I think there is a technical issue. So sometimes you can type your question to the Google Meet chat. Still not. Januka, I think you can see the question.
I see a question from Padme. Can you explain the cause of intraplate shaking? So what do you mean, actual shaking, or are you talking about earthquakes? Yeah, so like I mentioned, Padme, faults exist, everywhere, right? These are weak zones in the crust, and you don't need a special case or special conditions for produce earthquakes in intraplate conditions. Intraplate areas are full of faults, and whenever the stress conditions are right, they go off. And no, I'm talking about intraplate regions. So just like you have a network of faults along plate boundaries that go off frequently, you have faults in intraplate regions as well. It's just that they're not going off as frequently as at plate boundaries. No, you don't need plate boundaries. It's just a fracture in the crust. Yeah, Dr. Munasingh is asking, do you think the majority of the Sri Lankan earthquakes are dynamically triggered by Central Indian Ocean earthquakes? I don't know, because no one has looked at them. I wanted to look at least the magnitude 8, whether that's dynamic triggering from the magnitude 8.6 event. I didn't have time before I started the presentation, but it would be really interesting to look at that. Look at that. But I think Pasan will have something to say about that in a couple of weeks' time.
Okay, thank you very much. And furthermore, questions? Is there any question?
Januka, there are about 17 students registered for seismology this year.
That is awesome.
Yeah. What is the message that you want to pass on to them? Give some advice to them.
Oh, this is a fantastic field to be in. Not too many people in Sri Lanka has studied seismology. In fact, I'm really encouraged by the uptick of students in seismology in the last 10 years. 10 people have gone on to do PhDs in seismology. And don't forget, I kind of, since you asked this question, I kind of remember something that Dr. Pitavella said once when I was an undergrad. It provides you an opportunity to get a real international education. Okay, don't miss that. there are many programs in the world that would happily recruit Sri Lankan students. So if you study seismology, this door is open for you. And I'm more than happy to help with applications as I've done in the past.
Oh, thanks, John. Thanks.
So, thank you very much. I think now we have reached our time limit. So therefore, I think for the time being, I would like to wind up this session. So first of all, Dr. Januka, thank you very much again for your very interesting and very impressive talk. So I'm grateful for your time effort you took to share your thought and the experience with us. On behalf of the Geological Society of Sri Lanka, please accept my sincere appreciation. So also, my sincere gratitude goes to Dr. Pasan Herat for his kind support to make success this event. In addition to that, all the executive committee members of the GSSL are acknowledged for their numerous contribution on this event. And finally, I would like to thank all the participants for your participation. I think we had a wonderful and fruitful time with Dr. Januka. So hope to meet you again during the next GSSL public talk. Stay safe and stay healthy. Thank you very much.
Thank you very much, Lalita. Thank you, Dharma.
Thank you very much, Januka. Thank you very much.